Welcome everyone for our second day. I hope everything is going well with you. If not, contact any of the organizers who are sort of around here. And let's, without any time wasted, let's just start with our next Panorama talk, Gordana Matic, talking about symplectic and contour topology in dimensions 4 and 3. Thank you, Gordana.
So I'm really honored to talk in this Hello call. And thank you for inviting me and giving me this opportunity to celebrate the work of my friends. And so Panorama, I have a different picture, but it's from Banff, so it's where a lot of work in this subject has been described, discussed, and so on. So it's one of my favorite panoramas. So my understanding of a panorama talk is that we will try to introduce basic objects in symplectic and contact low-dimensional topology, like symplectic structure, contact structure, open book decompositions, Lefschetz vibrations, and then discuss the connection between the contact structures and the symplectic structures, which are symplectic fillings and contact type embeddings. And then I'm going to try to talk about basic questions and history, and I'm going to try and bring us closer to recent results. And naturally, there is too much to cover, too many things one should talk about, and there is no time, and I'm not an expert on a lot of it. And so, excuse me for any missed references, directions, and so on. We start with the symplectic 4-manifold, which is a 4-manifold equipped with a closed non-degenerate 2 form. There is a Darboux theorem that says that locally we have always coordinates so that omega looks like this, so there are no local invariants, so we often talk about symplectic topology rather than symplectic geometry for that reason. Basic examples are R4 with the form up there, cotangent bundles to surfaces, CP2, and any complex surface in CPN that will inherit the symplectic structure from CPN. So there are some necessary topological conditions on X to support the symplectic structure. A simplest one from algebraic topology is that B2 plus has to be 1 mod 2, so S4 and CP2 connect some with CP2 have no symplectic structures. Then there from gauge theory, from Donaldson, Seiberg-Witten, and so on, there are results on symplectic manifolds. And in particular, Taubes proved that if X is symplectic, then the Seiberg-Witten invariants are non-zero. And so, for example, certain kinds of connect sums don't have symplectic structures. And the simplest one I could think of is 3 connect sums with CP2. So this Taubes work was used by Finteschel and Stern to construct many exotic surfaces that are not symplectic. They also constructed many that were symplectic. Stipschitz and Szabo have constructed many small exotic manifolds that are symplectic. There are myriad other results on exotic manifolds obtained from symplectic manifolds, so too many to mention, and I will mention some later. So we're going to connect this with contact 3 manifolds, and so a contact 3 manifold is a manifold equipped with a nowhere integrable 2-plane field psi, which can always be represented by a kernel of one form, and one form that has this property of lambda h d lambda being the volume. So this is sort of an odd dimensional version of a symplectic condition. So again, locally, all contact manifolds are the same, all contact forms are the same. So we talked about contact topology. And a basic example is S3 in C2 with the contact planes given by as complex planes tangent to S3. And similarly, a link of a complex singularity, which is if we take a complex surface in C3 or in some other Cn that has an isolated singularity, and we take a small sphere around that singularity and intersect it with a surface, then the planes, like up in the case of S3, give us the complex planes give us a contact structure. So while there are topological conditions for existence of symplectic structure, there are none for existence of a contact structure. So in the 70s, Martinet and Lutz proved that every homotopic class of a plane field on any 3 manifold supports a contact structure. And globally, however, there are, so going back to this local global dichotomy here, locally they're all the same. By Martinet and Lutz, they exist everywhere on all manifolds, but globally there is a tricky thing because there are non-isotopic contact structures on R3, which was proved in 1983 by Benekin by looking at these 2 contact structures that I put down here, the standard one in the bottom and the one that is twisting around radial axis by the one form described over there. If you didn't see this before, I don't have a picture. But so I don't know how that happened that I don't have a picture, but I don't. Okay, I'm making this hard. So I want to talk, so this talk is supposed to be about the connection between the contact and the symplectic world, and we know that any oriented 3 manifold is a boundary of a 4 manifold. So the question is, can we promote this fact to consider it as a symplectic contact question? So can we find a 4 manifold X and a symplectic form on it W so that M3 and Xi are somehow compatibly the boundary of X4 omega? So of course, if I drop Xi and omega, then this can always be done. But I want to have some compatibility conditions. So there are various versions of compatibility. So the simplest one is that we could require the 2 form omega when restricted to planes of Xi on the boundary to be positive. And it's called weak fillability. Strong filling is if we assume 1, but we assume more, that is that in the neighborhood of the boundary, the form omega is d lambda of R form lambda. Remember, lambda d lambda was non-degenerate, so d lambda is non-degenerate. So we want it to be omega in the neighborhood of the boundary. And actually, we want there to be a vector field V so that this lambda is determined by omega in the vector field V. So if we require this omega equal to d lambda condition on all of X, then we call this exact filling. And this happens in a case when we have a so-called Stein filling, which is when X is a Stein domain. A Stein manifold is non-compact. It's an affine subvariety of Cn. But when we bound it to a finite radius, in some sense, then we call this a Stein domain. And on the boundary, there is a contact structure. And we want this to be compatible we want this to be our contact structure. So we call a contact manifold fillable if it has what we call a convex filling, which is that condition about the vector field pointing out of the manifold X that has the appropriate condition. So the question is, do all manifolds have fillings? This is now our question. All 3 manifolds have smooth 4-manifold fillings, do all contact 3 manifolds have symplectic fillings? And the answer is no. And it comes from the following dichotomy introduced by the Ashberg. He noticed like there is a difference between that standard and over-twisted and twisting contact structure on R3 that I described, in that the twisting contact structure, as it twists, comes back to be tangent to a disk in our XY plane. And when there is such a disk in a contact manifold, Ashberg called this manifold over-twisted. And what Bannekin basically proved was that the standard contact structure on R3 was tight, and therefore the two were not the same contact structure. So Gromov and Ashberg, using pseudo-holomorphic curves, proved that any fillable contact structure is tight. So any over-twisted contact structure cannot be a boundary of a symplectic manifold. So there is more of a difference there. Ashberg showed that tight contact structure exists in only finitely many homotopy classes, and by Lutz, these over-twisted structures exist in every homotopy class. Ettner and Honda showed that tight contact structures don't always exist, so they constructed first examples, and there are more later. And Ashberg showed that homotopy implies isotopy, but for tight contacts, but homotopy implies isotopy for over-twisted contact structure, but also that it doesn't imply it for tight contact structure by producing examples on the 3 torus, and then Liska and I produced some examples on homology spheres. So again, with respect to this being filled by symplectic manifolds, the contact structure, therefore, if they're tight, they could be fillable. They could be weakly fillable, strongly fillable, exactly fillable, or Stein fillable. And all of those inclusions are real, actual inclusions. Ettner and Honda found tight contact structures that are not weakly fillable. Ashberg had those non-isotopic contact structures, giving examples of weakly fillable that are not strongly fillable. Gigini had examples of strongly fillable, not Stein fillable, and Bowden made a distinction between exactly fillable and Stein fillable. So this was like being a boundary. The question is, can we embed a contact manifold into a symplectic one? So we say that the manifold is a submanifold M in X is of contact type if there is a Liouville vector field, namely a vector field that's stretching omega that is transverse to M. So if we have such a manifold, such a 3-manifold in a symplectic X, then this manifold has a contact structure given by the lambda that in the neighborhood of M has the property that d lambda is omega. And when we split this closed manifold into 2 pieces, we have 2 symplectic manifolds which have a boundary compatible with psi in 2 essentially somewhat different ways. So we talk about convex filling and concave caps for those 2 parts. And a lot of work on exotica and on various other questions came from finding fillings of a 3-manifold and then finding a convex cap for it. And so the existence on concave cap is due to work of starting with Gay and then Eliashberg and then Etnar Honda and so on. And it gave some very important applications to property P by Kronheimer and Rufka. And so the questions that we want to consider are existence of fillings for a contact structure, existence of contact type embeddings, and difference between types of fillings that are clearly questions. We'll try and talk about some of them. So to relate the two concepts more closely, I want to talk about two concepts that are related to contact and symplectic structures and relate the contact and symplectic structures to each other. And for contact structures, these are open book decompositions. And for symplectic structures, these are Lefschetz fibrations. So let me first talk about the open book decomposition. So what's an open book decomposition for a three-manifold? So first of all, in the three-manifold, you find the link that I'm going to call B. And if vibration of the complement of B over S1, we call BB because we call it the binding. And the preimage of a point theta under the projection and under this vibration pi is what's called a page. And maybe I should put it like this, everything up. So the closure of the page contains the binding, and then it's a closed page. M3, because this vibration, I'm experimenting here, because this vibration is a vibration, there is a monodromy, phi, that we can record, and with that monodromy, the complement of B is a mapping torus of the page, not a closed page, but an open page. If we close the page and introduce some sort of squeeze the boundary off down to a point, we get our manifold M. We can also think of this as M3 being divided into two pieces. The complement of the neighborhood of page, which is a mapping torus, which is often called the paper of the open book. And then there is the neighborhood of the binding, which is the spine of the open book. So in 1975, Thurston and Winkelkemper given an open book decomposition for a three-manifold, which, by the way, exists for any three-manifold. They constructed a contact structure psi that we call carried by this open book. And by constructing one form lambda that was a contact form, that was an area form on each of the pages and was transfers to the boundary, to the binding. So this was another construction different from Martinet and Lutz for contact structure on any three-manifold. So in 2000, Emmanuel Giroux proved the converse, that any contact structure on a three-manifold has a compatible open book decomposition. So comes from this Thurston-Winkelkemper construction. And moreover, that there is a one-to-one correspondence between contact structures on M, modulo isotopy of contact structures, and open book decompositions on M, modulo positive stabilizations. Positive stabilization is basically taking an open book and adding to it increasing the number of boundary components and putting in an extra positive Dane twist. So the natural question is to ask is how the properties of psi get reflected in the open book. So here's a theorem of Eliashberg that addresses that. If a contact structure Xi on a three-manifold M is carried by an open book such that its monodromy factors is a product of positive Dane twists, then Xi is Stein fillable. Then there is a theorem in the opposite direction by Giroux, Loy-Pierre Galini, and Agbulut and Osbachi that says that if X is Stein fillable, then it is supported by some open book with positive Dane factorization into positive Dane twist. So, remember that there is a plethora of Stein examples, and they come from lots of them come from isolated singularities of a complex surface, say in CP3. So let's say we have a polynomial that has an isolated singularity in the origin, and we intersect it with a small sphere, getting a three-manifold on the boundary. And perturbing this equation gives us a smoothing, which is called sometimes smoothing, most often called a Milnor fiber, which is actually a Stein filling. This perturbation doesn't do much on the boundary. It keeps the contact structure the same, but it gives us a nice smooth filling, which is a Stein domain. There is another thing you can do with complex singularities, which is take the singularity and resolve it by blowing it up, by doing a resolution of singularities. And then this point becomes a bunch of surfaces inside of the four-manifold or complex curves with, they could have genus and self-intersection, and those numbers for every I determine the neighborhood of that surface. And on the boundary, we're going to have the same manifold as the link of the singularity M. And this construction, there is a construction using this story that gives us a lot of exotica, which is to replace the neighborhoods of divisors by simpler fillings. So we take a neighborhood of a divisor, so we have this singularity in the surface Z, we resolve it, and then for a part of the resolution, we do what is called rational blowdown, namely we find the part of this singularity that bounds the contact manifold, so that that contact manifold has simpler topology. For example, if M is a rational homology sphere, we can try and find W that is a rational homology ball and plug in that W instead of the neighborhood of the singularity. So the story is called rational blowdown. It was invented in smooth category first by Fintushel and Stern. Symington showed that it was a symplectic operation, and then John Hill Parks, Dipshit Sabo, and many others used this to find exotica and to find small exotic manifold. There are other constructions about plucking out a bit of the surface and replacing it with something simpler, giving other exotic four manifolds. But that's a topic for yesterday and for later. I'm gonna steal something from a topic for tomorrow, which is on Hilbert-Fleur homology. So I'm going to talk about the Ozat-Szabo contact class. So in 2002, given this Giroux theorem that every contact structure has an open book, then Ozat and Szabo used this open book to construct a special Hilbert diagram for the manifold M and a special element in the Hilbert-Fleur homology for minus M that we today call the Ozat-Szabo contact class, and that has properties that this C of Xi is 0 if Xi is over twisted, and it is non-zero if psi is Stein fillable. Therefore, C of psi gives us obstructions to fillability. Okay. So there are versions in HF plus version of Hilbert-Fluor homology, in the twisted coefficients version, and there are so many results on contact structures that come from this contact class that are too many to try and list them, but I'm still going to try some. So in 04, Liska and Stipschitz looked at tight contact structures on rational surgeries, on knots, and showed that some surgeries support no tight contact structure. Oswald, Stipschitz, and Szabo looked at the C plus version for psi supported by planar open books. And they showed the existence of contact manifolds that do not have planar open books. A planar open book is, from the genus point of view, the simplest possible page of the open book, which is a disk with some holes punched in. So there was a question whether every contact structure supports such an open book. Ettenauer proved that every over-twisted contact structure supports such an open book. There's a lot of simple links of singularities that support such open books, but there's a proof by Oswald, Stipschitz, and Szabo that there are manifolds without planar open books. To these days, we still don't know whether there are any manifolds that require genus bigger than one open book. So some interesting questions there still. So other uses that in 04, Gigini proved that weakly fillable is different than strongly fillable, and that strongly fillable is different than Stein fillable. Generalizations are contact classed in sutured Fluor homology by András Juhász. Sutured Fluor homology was defined by András Juhász, and Honda, Kazez, and I defined contact class in it. Bordered Fluor homology was defined by Lifshitz, Oswald, and Thurston, and Ali Shahi, and a whole bunch of other people defined contact class in bordered Fluor homology. Zarev defined a combined version of sutured and bordered Fluor homology called bordered sutured case, and Min and Varvarezos in 24 defined a contact class in that setting, and they proved that a tight contact structure with half Giroux torsion can have non-trivial contact invariant. This uses some, yeah, well, maybe. Then there is there is a refinement, not a generalization, of a contact class that we call spectral order, that's in my joint work with Kutluhan, Van Han, Morris, and Wang, that gives another obstruction to Stein fillability that can be used when contact class is non-zero. So this is the story of open books and how open books define this wonderful invariant called contact class that was defined by Oswald and Szabo. And so I want to talk now about the results on Stein fillings and how they connect to the open book decomposition. So to do that, I need to talk about Lefschetz pencils and fibrations, an idea that comes from complex geometry. So a Lefschetz pencil on X requires us to pinpoint a finite set of points B in X, and a fibration and a map from F from the complement of B into S2, which is a fibration, and then another finite set of points A in the complement of B, so that off of that set of points, the fibration is really nice, and it's a subversion, and at those points AI, we have a singularity. So here's a picture. Lefschetz pencil has these points B where if we remove them, we have a nice map. And it has some singular points that are in orange here. And to go from left-shaped pencils to fibrations, we blow up at those green points, introduce some exceptional fibers, and then we get the fibration with singular fibers at orange dots. And that's the left-shaped pencil fibration idea. So a more true to the dimension is what we have is we have a sphere, and in it we have a few points. After we blow up to get an actual fibration, every fiber is a surface of some genus, and a singular fiber are singular surfaces where each one has, it can be obtained so that each singular point lives in a separate fiber, and those fibers are normal crossings. And they come along a path from a regular fiber to a singular fiber. There is what we call a vanishing cycle that contracts to a point. So Donaldson in 1999 proved that every symplectic manifold supports a left-shaped pencil, and after blowing up this pencil, it supports a left-shaped vibration. And because of the structure of the neighborhood of a singular point that's well understood as a surgery on a product along this, adding a handle along this vanishing cycle, Gomf proved that if a four-manifold supports a left-shaped pencil structure, then it has a compatible symplectic structure. So how do we, here are theorems for closed manifolds. Well, how do we parlay that into something for manifolds with boundary? So when Y is a filling, then the idea is that we embed Y into a closed manifold. So we have to start with a Stein filling, a Stein domain. We embed it into a closed manifold. In '97, Paolo Lisca and I needed that for a reason for proving some contact structures were not isotopic. In '02, Eli Ashberg and Etnar Honda produced symplectic caps. And now once we have this Stein domain inside a closed symplectic manifold, we can apply Donaldson's procedure to X so that these points in A are in a complement of our domain Y, and the fibers are transfers to the boundary. To do that, we really need a Stein structure. So theorem of Loy-Piergalini, Alvolutos-Bacci is that if Y is a Stein domain, then there is a left-shaped vibration with fibers that are surfaces with boundary. So we have a boundary, a Stein domain, we construct this left-shaped vibration, and in this construction, we have vibration now over D2, there is a natural decomposition of the boundary of this four-manifold into the vertical parts and the horizontal parts. The vertical parts are the page, are a bundle with this thing we're going to call page, which is the fiber of our vibration, with some monodromy phi, and we add the base times the boundary of P. So this is the paper, what we call paper, and this is what we call the binding. And when we have this left-shaped vibration structure, then this monodromy factorizes into Dane twists around these vanishing cycles, and these are positive Dane twists. So so this comes from Donaldson's theorem, and by this embedding, and it's really a structure on a on a Stein domain that's been used a lot. There is a different approach to understanding Stein domains is that going back to the proof that fillable contact structures are tight, the proof was done by Gromov and Eliashberg by assuming you had an over-twisted disk in the manifold and trying to like push it into the interior. And so that sort of filling by holomorphic disks was promoted in 2010 by Wendell to planar open books, and he showed that if a contact structure admits a planar open book and we have a strong symplectic filling, then this strong symplectic filling is the formation equivalent to a blow-up of an allowable Lefschetz fibration with that given open book on the boundary by like pushing those pages of the open book to the inside. And this showed that every Stein filling is of M psi is compatible with that same open book. So that, therefore, the Stein filling of M psi corresponds to factorization of its monodromy into positive Dane twists. So finding one open book with planar pages gives you all the possible factorization of its monodromy. And if you understand all the possible factorization of its monodromy into positive Dane twists, then you understand all the Stein fillings. A remark here is that there are Stein fillable contact structures that are supported by open books that do not have positive factorizations of the monodromy. There are examples in, definitely in small genus with small numbers of boundary components. One counterexample is, there are many examples, too many to list, so I didn't list them. I maybe could have, because I'm seeing that I have a lot of time. But so, as I said, Wendell's technique is filling the pages of the open book and pushing this idea further. Lisi, Van Horn, Morris, and Wendell in 18 and 20 to deal with minimal symplectic fillings of planar open books. Foliated the filling by the moduli of the pages, and they produced singular Lefschetz fibrations. And so this, after pushing it, so you push with these pages, and then you come to a problem, and the problem can be that you have singular Lefschetz type fibers, and then something they called exotic fibers. But in the situation when there are no exotic fibers, what you get is really something that's deformation equivalent to a Stein manifold, because you have produced a manifold, you have produced a Lefschetz fibration. Yeah? So in 2024, Hyun Kim-min, Agnew Arroy, and Luya Wang used these so-called spinal open books with exotic fibers to force the fillings to be complements of multi-sections in bordered Lefschetz fibrations, and I think Luya will be talking about something like that today. Just to say what's happening here, when there are no exceptional fibers, what we have is a fibration with just singular fibers of Lefschetz type, and now the base is possibly not a disk, so it's got some geometry, some genus to it, and but still we have a filling that has a boundary that is our contact manifold, and on this boundary now we don't see an open book because the base is not a disk anymore, but we see a manifold with a surface with boundary with some genus, we can still break up the boundary tree manifold into paper and spine, paper still being an S1 bundle with a fiber P and with some monodromy phi, but now the other portion is, is the spine, and this spine is the base manifold times the boundary of P. So this kind of decomposition, Lisi, Van Hon, Morris, and Wendell called the spinal open book. And in 2020, they have a construction called spine removal surgery, where they take this spine and replace it and kind of kill it, and they produce some contact structures that are not Stein fillable. So the question is, one question one can ask is, like, there are Stein fillings, non-Stein fillings, how do you construct one in the other? And the other question one can ask is, can we classify Stein fillings? So for simplest isolated complex surface singularities, the Stein fillings are deformation equivalent to smoothings, Milnor fibers, and there's a classification. And this is not true in general, so a lot of classification results, due to Liska and so on. And it's, however, not true in general that every Stein filling is a deformation equivalent to a Milnor fiber. So if a resolution contains the curves of genus bigger than 0, then one can construct Stein fillings that are not Milnor fibers, because genus bigger than 0 lets us construct fillings. This was mentioned yesterday that have an algebraic obstruction to being Milnor fibers, and so this was exploited by Osbachi and others. So if we have in that resolution of the singularity, if we have curves that contain that have some genus bigger than 0, then we have infinitely many Stein fillings. So the simplest isolated complex surface singularities were classified. So we're going to hear later today about more general so-called rational singularities, meaning there are no higher genus curves in the resolution. So Plamenevska and Starkston and Becke and Plamenevska and Starkston analyzed the special kinds of rational singularity links and found Stein fillings that are not Milnor fibers, and I think we're going to hear about that later today too. So I'm done early, so we have more time for coffee. This is the Panorama of Budapest this time, and thank you again, and oops, mistake.
Yeah, thank you very much, Gordana. And we have time for questions if you have any. And I'm ready to run. All right, no questions. Thank you, Gordana. So thank you again for the speaker. But before that, I would like to tell you what's going to happen. We were planning to have a half-an-hour break. So we're going to resume after coffee at 10:30, when we're going to have three lighting talks. And then after that, Laura is going to give a talk, Laura Starkston. Okay, so see you soon.
Great. Well, thank you so much for having me here. It's really an honor to be speaking here. So Gordana gave the panorama and explained a lot of things that are going to be very helpful for me. And Marcy gave the snapshot. And so this will be the documentary, I suppose. So yeah, this is based on joint work. Maybe 2 papers that Olga and I did together, and then the most recent one is with Marcy and Olga as well. As Gordana explained, if you look at isolated complex surface singularity, one of the kind of big questions in singularity theory, algebraic geometry that you can try to study is what are the ways that you can deform that singularity to make it non-singular. And so in our terminology, we call any smoothing, any deformation to something smooth, a Milnor fiber. The other important definition is the link of the singularity. So when you have a algebraic thing, it's cut out by a bunch of polynomials in some large dimensional Cn. So you've got some polynomials cutting it out, and in that large Cn, I'm going to take a ball whose center, a small ball whose center is at the singular point. And if I look at the boundary of that ball, it's a sphere, and it will intersect my complex surface. So complex 2-dimensional means real 4-dimensional. So I've got a hypersurface cutting my 4-dimensional thing transversely, so that's a 3-dimensional manifold on the boundary. So my red dots indicate a 3-dimensional manifold, and they come with a contact structure by looking at the space of complex tangencies to that 3-manifold. So the thing you get if you look at the ball around the singular point or you look at the ball around the Milnor fiber, you have the same 3-manifold on the boundary. So, and then the other way to kind of look at a thing that fills that contact manifold or look at something associated to that singularity is to look at the resolution. So you blow up at the singular point until it's not singular anymore, and you look at the configuration of exceptional curves that come out of that. And in general, we can encode that by a graph with some decorations. So there's some graph, and I've put numbers which indicate the self-intersection numbers of those corresponding exceptional divisors, and the edges indicate how they intersect each other. In general, you should also specify the genus of each exceptional divisor. In my setting, I'm always going to look at rational singularities where the genus is 0. So I didn't put any genus numbers. So in general, these smoothings provide symplectic fillings of that contact link of the singularity. So this is what Gordana and Marcy kind of both explained. And the question is, are there other symplectic fillings besides these Milnor fibers and the resolution? So I'm going to give a few more details on Gordana's summary. So for some basic classes of singularities, the answer is no. The Milnor fibers kind of give you everything. So if you look at simple singularities, simple elliptic, cyclic singularities, which are the ones whose boundary is a lens space, or quotient singularities, there are all of these results that say that the only symplectic fillings are the ones that are given to us by algebraic geometry. And for non-rational singularities, usually there are lots of examples where you can find symplectic fillings which are not can't be Milnor fibers, with maybe some topological invariants that give obstructions. And there's also lots of examples where you can find infinitely many symplectic fillings, and the general expectation is there should only be finitely many Milnor fibers, but there's a slight subtlety there because there's a difference between saying that the kind of equivalence relation for singularities, which is analytic equivalence, and topological equivalence, which is kind of saying like the link of the singularity is the same contact manifold. So let me maybe just not say anything further unless someone has a question about it, and then we can talk later. But the point is there's kind of this in-between land between these like really basic classes of singularities and these like much more complicated singularities, which are the sandwich singularities. So let me show you what these are with an example. So Marcy explained that the sandwiched graphs are these ones where you can add these -1 leaves so you can blow down to nothing. So the one-sentence description of sandwich singularity is they're singularities that birationally embed in C2. So you could think of that as saying the resolution graph, the plumbing, embeds into a blow-up of C2. So in practice, you take your resolution graph and you add some -1s here, so you can see this example. If I kind of blow down the red -1 spheres that are up there, I kind of switch from the dual graph notation to the curve notation for the blowdown. Then if you just ignore the arrows for a minute, the -3 becomes a -1 as I go from left to right on the middle row, and then I have a new -1 sphere that I can blow down, and I kind of keep going each time I have a -1 sphere that I can blow down until I get to nothing. And the kind of important discovery of de Jong and Van Straten was that you can, for these sandwich singularities, study their deformation theory, their smoothings, their Milnor fibers, by studying the deformation theory of curves, algebraic curves in C2. So they have this process by taking this surface singularity and associating a singularity of a plane curve germ, singular plane curve germ. So the way you get the curve is for each of these -1 curves, you put a little smooth disk that's dual to that -1 curve, that intersects it transversely in a point, and you just track those disks as you go through the blowdown process and see what happens. So in this setting, my little arrows represent the disks, and so when I first blow down the red -1 curves, they just land on the next -1 curve. But as I keep blowing down, at some point they start to intersect each other transversely, and then another blowdown causes them to intersect each other tangentially. Another blowdown causes them to intersect even more tangentially, so it's like a degree 3 tangency. And then at this kind of second to last step, they're actually tangent to the exceptional curve, so when I blow that down, they actually become singular. So instead of being smooth disks intersecting tangentially, now they're kind of two cuspidal disks intersecting with some degree of tangency. And so basically what I need to remember is kind of what are the singularities of each of those disks, and how do they intersect each other? What kind of degree of tangency do they all intersect each other? So this de Jong-Van Straten theorem is that the smoothings, the Milnor fibers of the surface singularity, are in correspondence with what they call picture deformations of the associated plane curve germ that you get from this blowdown process. And the value of this is studying algebraic curves in C2 is way easier than studying these kind of abstract surface singularities in high-dimensional affine space. So you've just got like some hypersurfaces in C2 now. So what Olga and I did was try to develop this correspondence for symplectic fillings. And so now we've got our link of our sandwich singularity, so that's our contact-free manifold. And now de Jong and Van Straten have associated a curve, this kind of singular plane curve, to our sandwich singularity. And I can look, just like I looked at the link of my surface singularity, I can look at the link of my curve singularity. So I take a 4-ball in C2, and I intersect that 3-sphere with the boundary of my, with my plane curve, and I get an actual link in S3. So link this time means a link in the classical sense of knots and links. So given that particular link, I'm going to define a generalization of picture deformation, which we're calling DJVS immersed disk arrangements. So the DJVS is for de Jong van Straten. So basically, we just have a collection of immersed disks inside of the 4-ball, which I'll think of as a disk times disk, where all the intersections between the different disks or self-intersections are transverse, but they don't need to be generic. They could be, I could have multiple sheets intersecting all at the same point. And then my other requirement is, because I'm thinking of the 4-ball as disk times disk, I have a projection onto one of these two-dimensional disks, and I want that projection to restrict to my curves to be a simple branched covering. So I might have some tangencies to the vertical fibers, and I might have these transverse intersections. And so what we showed is a kind of analog of the de Jong van Straten correspondence, which is the symplectic fillings of this contact link are in correspondence with the DJVS immersed disk arrangements, which have this fixed boundary link, which is agreeing with the link of my plane curve germ. So the main difference between the symplectic setting and the algebraic setting is that for de Jong van Straten, these picture deformations have to be actual deformations. So I start with my plane curve germ, and I have to have like a kind of family which immediately deforms it into this sort of new arrangement. Whereas with the DJVS immersed disk arrangements, anything that has the same boundary, it doesn't matter if it kind of came from a deformation, will work to construct a symplectic filling. Any questions so far? Sorry, I'm gonna, if maybe I'm making more work for Vera, but okay. If you have a question, feel free to interrupt me. So let me just give you a little taste of what goes into the proof. So for these, so there's kind of two directions of the theorem, right? Because it's a bijective correspondence. So if you want to start with a DJVS disk arrangement and construct a filling, what do? So you have these curves sitting in C2, which have a nice projection to one copy of C. And what we're going to do is, at any place that we have a transverse intersection, we'll blow up at that point. And maybe a sort of technical detail is there are these marked points at each of these transverse intersections, and maybe some other marked points around that we might blow up at as well. In this example, I've only marked transverse intersections. So at each of those transverse intersections, I'm going to blow up, and I get an exceptional curve. So now I'm in a blow up of the 4-ball, and I'll take a neighborhood of the resulting proper transform, and I delete that neighborhood. And that's supposed to give me my symplectic filling. So if you look at the de Jong van Straten setting, then they kind of do the same thing for their picture deformations. They blow up, they take the complement of the proper transform, and that gives them their Milnor fiber. But they're using algebraic geometry tools to say that this is actually a Milnor fiber. So we have to use symplectic tools to show that the resulting thing is actually a symplectic filling of the contact manifold that we care about. So the tools that we use are these nearly Lefschetz vibrations that generalize standard Lefschetz vibrations. So this is the generalization from Min-Roy-Wang that Luya will probably be talking about much more very soon. So in our setting, we're not going to use the full generalization, but we need this particular additional thing that's allowed to happen. So in a Lefschetz vibration, you're allowed to have these kind of singularities where your singular fiber has what looks like a kind of normal crossing situation. So there's a particular model for Lefschetz critical points in the projection. What we need to add is the situation where we've got our fiber, which in our case is just the plane. So in C2, we've got the projection from C2 to C, and the fibers of that are just planes. And we're going to take the complement of the proper transform, so that's going to cut holes in the plane. So our generic fiber is one of these planes with holes, and the number of holes is, in this case, generically 3. But whenever I have a branch point of my surface, where my surface projects down via my branch covering, whenever I have an actual branch point, then what happens in the fibers, these vertical fibers, is 2 of these holes will join together into one. And so I have fewer holes. My fiber has changed topology. And that's not a normal thing to happen in a vibration, and it's not a Lefschetz singularity. But what it is something that is now called an exotic fiber, and it fits into the framework of these nearly Lefschetz vibrations. So there's kind of a model for these exotic fibers which says that if you have a nearly Lefschetz vibration, then you have the kind of corresponding symplectic structure, generalizing the kind of Gomf symplectic structure on a Lefschetz vibration. And then we need to go in the backwards direction. So from a disk arrangement, we've produced a symplectic filling. I've brushed under the rug some details about why the contact structure is the one that we want it to be, but it is. And now we want to say that all of our symplectic fillings actually arise this way. And this is where we need the pseudoholomorphic curve analysis that says because we have a planar spinal open book, all of the fillings are actually arising as nearly Lefschetz vibrations which fill this particular spinal open book. So every filling comes from a nearly Lefschetz vibration. Every nearly Lefschetz vibration is going to show up as a complement of a multisection in some Lefschetz vibration, planar Lefschetz vibration. And in the setting of spinal open books that we have, that means that it has to be the complement of a multisection in a blowup of C2. So that's how you get kind of this correspondence between the symplectic fillings and these disk arrangements. Okay. No, I'm still going, but if you have a question, you can interrupt me. All right, so kind of one of the outcomes that we get from this correspondence is that it allows us to study the difference between the Milnor fibers and the symplectic fillings using these kind of disk arrangements. So the kind of older work that Olga and I did, we found these kind of unexpected fillings which are not diffeomorphic to Milnor fibers, from these kind of pseudo-line arrangements. So it's not a straight line arrangement, but it's like wiggly lines in the plane that can't be realized by any kind of complex line arrangement. And actually, we need something a bit stronger than that. So we were able to find these kind of pseudo-line arrangements that we could show could not be realized by any picture deformation, the kind of deformation that de Jong and Van Straten allow. And thus, we're able to produce these symplectic fillings that can't correspond to Milnor fibers. And we kind of, so in the kind of more recent work, instead of just looking at these pseudo-line arrangements, we want to be able to study disk arrangements where we actually have some branch points in the picture. So when we do this projection, it's not just a bunch of smooth components with no tangencies to the vertical fibers. So in order to study these things, we're looking at some kind of surfaces in four-dimensional space with singularities, controlled singularities. And we want a way to represent these diagrammatically. So the way that we do this is through something called braided wiring diagrams. And this is a generalization of what Arvola originally called braided wiring diagrams in order to study complex line arrangements. So our generalization is going to allow these tangencies, which are the branch points of our surfaces. So what this is it looks kind of like a braid, except you're allowed to have singularities. And so we've got crossings, we've got these kind of marked points, which represent the singularities. And what the braided wiring diagram is literally is it's a three-dimensional slice of our four-dimensional space, which contains our surface. So we take our four-ball, we find some like three-dimensional slice, and our braid lives inside there as the intersection of our surface with this three-dimensional slice. And so the picture on the left is meant to be kind of the base of my projection. What I want to do is for any interesting thing that happens in my surface, whether it's a branch point or an intersection, transverse intersection, I want that point to be in this slice. So if I'm able to just take a straight line in my base that goes through all of these, the projections of all of these interesting points, I'll take a straight line. If it needs to move around a little bit, I'll just follow, connecting the dots to make sure that I pass through anything interesting that happens in my curve. And then I look at the preimage of that interval under the projection, and that's my three-dimensional space where my braided wiring diagram lives. So inside of that interval times R2, or interval times disk, I see the intersection with my surface as this kind of singular braid. So in this case, in the middle picture right now, on the far left, you can see one of these kind of things that I use to indicate the tangency. So it looks like the two sides are tangent to each other. And then on the bottom, there are some actual intersection points that are marked with a black dot. And then there's also some like genuine crossings that are part of like a normal braid. And the actual crossings, the normal braiding part, is telling me how, what happens with the surface, what's going on with this isotopy class of the surface as I connect from one singular point to the other. So in order to go from this kind of wiring diagram to understand a whole surface, I kind of just want to expand outward, push this three-dimensional slice a little bit backwards and a little bit forwards and see what happens. So near the singular points, I have a kind of standard model for what happens near a singularity. And if I push it a little bit backwards, I know that my intersection, my transverse intersection, is going to break into a particular crossing if I move backwards, and the other crossing if I move forwards. So, you know, this is how intersections work if you do a movie, right? You start, the sheets get closer and closer, they hit, and then they pass each other. So if I look at kind of the push-off to the back and the push-off to the front, I get actual braids, normal braids. And if I want to know what the link of this kind of now singular curve configuration is, what the link is that goes all the way around the whole thing, I look at the part on the back, which is in this picture on the top, and I read it backwards, because if I go around my circle counterclockwise, you go around the back right to left, and then I go around the front push-off, the one that's on the bottom, forwards, left to right. So I start at the top right, I go to the top left, and then I go down, and I read from left to right on the bottom. And that's the braid that I get by going all the way around. And that braid is super important because that's what tells me whether I am looking at a disk arrangement which is filling the correct link. So it will give me a filling of the contact-free manifold that I want. All right. Okay. Yeah. I don't make the rules.
I'm not very familiar with this definition, so I'm not entirely sure if this question is well posed, but like doing this push-off, is it possible to do, like if you have multiple intersection points, is it possible to do, like, is there any interference with that in having to like resolve those singularities simultaneously?
Yeah, so you mean like if you have multiple
like intersecting
branches all intersecting at the same point. Yeah, so you just have a model for if you have like 3 pieces intersecting together, the model is like 3 complex lines intersecting at a point. And essentially what happens is when you push off in one direction, you get a half twist in one direction, and in the other direction, you get a half twist in the inverse half twist on all those strands.
Or maybe, I'm not sure if, maybe that does answer my question, but maybe I didn't say it quite well. Like, if you have multiple, so here you have like multiple singularities, and you're taking like a uniform push off of the whole braid, is it something that's done locally?
Yeah, right. Okay, so for each singularity, you've got a local model, which shows you what the local push-off will be. And then to get the global thing, you kind of concatenate this stuff. So anywhere where you have like braiding, or even just like trivial braiding, when you push that off, nothing happens. So like there's no singularity, so if you push it a little forwards or a little backwards, that's just a smooth part of the surface. It doesn't change. And then where you have the singular points, you replace the singularity when you push it a little bit by the kind of way that it gets resolved if you push it a little forward or a little backwards. And then you just like concatenate it all together, and that's how you get like this long braid on the top and long braid on the bottom.
Okay,
Does that make more sense?
That makes sense. So like, yeah, as you push they all will change in the same way, so it's all compatible.
Yeah, so there is kind of a convention that we set, which is like, if I ever have a tangency, I'm going to fix a particular model for how that tangency sits in space, and so that the resolution, when I push it a little backwards, is always going to have crossing on the back side and no crossing on the front side. So that's actually a particular choice of convention, and we stay consistent so we don't mess something up, basically.
Okay, thank you so much.
Yeah.
Thank you.
Anything else while we're at questions? All right. So when we have a kind of diagrammatic way of looking at something, a nice thing to be able to do is to have a sort of calculus for doing moves on those diagrams that preserve the thing that we care about. So depending on your point of view, you may be interested in trying to preserve something like the isotopy class of the surface, like the equisingular isotopy class of the surface, or for this context, the thing that we mainly care about is preserving that total link that we go around in the big circle along the boundary. So we don't have currently a complete calculus for either of those equivalence notions, but we do have moves that do preserve the thing that we care about and are useful. So that's where we are so far. So this is an example of some kind of move that involves the interaction of a tangency intersection and a tangency singularity and an intersection singularity. So if you look, let's just look at the top one with the blue and red. On the far right, there's a double point intersection, and then there's this tangency. And the question is, can you move that intersection point past the tangency by pushing it up to the higher strand? And so this move tells you you can, at the expense of modifying the braid a little bit. And the picture below with the red and green is actually the same move, but it's just like the inverse of the move where I've concatenated with a little more braiding. So this is like an example of a move, and we can check that this is something that preserves the total monodromy. Like, even if this was just part of the diagram, if you find this part of your wiring diagram anywhere in the picture, you can do this substitution, and the total monodromy will be preserved regardless of what comes on the left or the right of this local picture. This is the proof. So if we want to show that it preserves the total monodromy, we look at the back push-off and we look at the front push-off. And so each of those are going to be some kind of braid. And so if you take the wiring diagram on the left and the wiring diagram on the right, you look at the back push-off, and you can stare at it and convince yourself that these braids are isotopic to each other. The two sides of the arrow on, let's say, back. And maybe easier is you look at the two sides of the arrow on the front, and those braids are also isotopic to each other. So if the back push-off and the front push-off give you isotopic braids, then if I insert that section of braid into my picture, then it will preserve that total monodromy. Okay, so then this is a kind of generalization of that move. If I've got lots of strands all intersecting at a single point, and they then all have a bunch of tangencies right after, I can kind of take this multi-point intersection and push it through all those tangencies to get it from the top to the bottom, or inversely from the bottom to the top. But there's, again, a cost of adding some braiding in. I won't show you the proof of that one, but it's the same idea, just more strands. Okay, and so this is the application that Marcy talked about. So for this particular family of sandwich singularities, we were able to find rational homology disk fillings, symplectic fillings, and there's kind of algebraic geometry reasons that these cannot have rational homology Milnor fibers. And so the symplectic fillings, because these are sandwich singularities, we're able to find the symplectic fillings with this calculus of braided wiring diagrams. So I think Marcy showed these pictures, but super fast. So maybe we get to take a few moments to actually look at what's happening here. So I've got kind of 3 steps at a time. So let's see, maybe I can figure out how to use the, okay. So the first picture here is kind of one that we know it represents a very standard filling, which corresponds to the resolution of the singularity. So this is like a very standard filling, and this is the corresponding wire diagram. And so then the first thing we do is, you see this like giant multi-point at the beginning. We're going to break that up so that the top half of the strands and the bottom half of the strands, they each keep their own intersections amongst themselves, but they intersect each other transversely. So it's like, these are my top half of strands, and these are my bottom half of strands. First, they intersect each other, like all at the same point where they all intersect themselves. And then I kind of like separate them out so that they intersect. Can I do this? You know, they're sort of intersecting all like this, and then I just kind of move these guys up. So this kind of diamond of double point intersections is now the intersections of all the top strands with all the bottom ones in a generic way. And then you've got kind of remaining, the bottom strands still intersect each other here, and the top strands, their intersection is now down here. That actually corresponds to a deformation. It's definitely not preserving the singularity types, but it is preserving the total monodromy because it's just a deformation of the lines. And then going from the second picture to the third picture, we're just taking the black strand up here and joining it with these guys that we're intersecting here. So we kind of just pass that strand through the intersection point, and now we've got a kind of less, the multiplicity of that intersection has increased. So these are a couple more moves that you can do to preserve the monodromy. Okay, now the top picture is the one that we just talked about as the bottom picture. So to go from the top picture now to the second one, we're doing some more moves of kind of sliding intersection points past each other. So here's another thing that you can do. You see this like intersection point, this last one has kind of a little bit less strands going through it than the other guys next to it. So I'm just going to kind of push him up and down until he gets past all these guys to move him out of the way. And he lands over here. And then I'm going to use the move, the crazy move that I showed you just before, to move my intersection points past tangencies. So these intersection points started on the bottom, and I'm going to flip them up past all these tangencies to the top. And there was some cost of adding some braiding at the end, which I actually haven't even drawn here. But that's okay, because if there's braiding at the very end of the diagram, it cancels itself out. When I go around the back, I get the inverse of the braid, and when I go around the front, I get that braid again. So the inverse and the braid, they cancel out. Okay, so we're getting a good sample of all the moves. And then this is where things got kind of tricky. So far, everything was stuff that if you kind of play around with this stuff and try to draw pictures on the plane, like on a flat piece of paper without braiding, if you've thought about it enough, you could come up with it without kind of knowing this braided wiring diagram calculus. But at some point, something tricky has to happen. So here, okay, the rest of these moves here are actually not so hard. So this one, we start to take these intersections on the top, and we want to take this like diamond of double points. Our goal to make a rational homology ball is to have kind of as few intersections as possible in some sense. And so all these double points are like wasteful. And so we take each of these kind of multi-points, and we're going to slide it to combine it with one of the strands in this diamond. So the first intersection gets combined with the light blue strand, the second intersection gets combined with the dark blue strand, the third intersection gets combined with the green strand, and the fourth intersection gets combined with the orange strand. So if you kind of stare at it, you can kind of see that we kind of move that intersection point close, and then just pass that strand instead of generically through all the things going through it, you just put it through that intersection point. And then we're kind of stuck with the red strand and the black strand still having double points. And so Marcy came up with this clever idea, which is maybe not going to look as impressive to you as it did to me, which is, I'm going to skip a few to the interesting part. So stuff happens, stuff happens. And OK, we end up here. Let's go at the bottom here. So we've got this kind of red strand, and we don't know how to combine it with this remaining multi-point singularity. And the problem is that the red strand intersects all the guys going through this multi-point here, except for the black one. And the black one, it intersects kind of instead below this tangency instead of on top. And in order to combine it with this multi-point, I need this point, this intersection point between the red and the black, to move up. So what do? We apply this move to push it through the tangency, and it lands up here. And we had to stick some braiding in when we did it. And this braiding is the thing that you would never have come up with if you were just playing around and trying to force curves to intersect in the plane in this particular number of intersection points. So if you knew the combinatorics you were aiming for and you just drew stuff, you would not have drawn this little braiding in here. And so that's what the moves were useful for. And the point is, if you don't have this little braiding in here, the total monodromy, the link of the singularity that goes around, is wrong. So using those moves is really important for getting the correct arrangement and kind of knowing that this actually exists. So yeah, so in the end, we kind of realized the configuration that we wanted. We have the correct combinatorics. And so we use this construction to build the symplectic filling from that. And that gives us our unexpected rational homology ball filling. All right, so I will stop there and open it up to any more questions that you guys have. Thank you.
So, any questions?
So this might be difficult without a board or something, but maybe you could say, is it easy to go from the resolution graph to the first braided wiring diagram that you had? Is that algorithmic?
It's algorithmic. Easy is another question, but algorithmic, the answer is yes, yeah. And it's kind of, yeah, so the nice thing about sandwich singularities is their resolution actually is a smoothing. And it's a particular smoothing that comes from a curve arrangement called the Scott deformation. And so there's a really nice diagram, wiring diagram, that corresponds to the filling, which is the resolution, which actually has no braiding in it. So it's kind of the simplest, nicest wiring diagram amongst all fillings. And yeah, there's an algorithmic process that's kind of related to just blowing up.
Other questions?
I have another question. So it seems like what was I going to say? This like total monodromy preserving move really looks like, you know, once you do the resolution or push it forward and back, it looks like a sequence of Reitermeister moves. So I guess like you said that, it seems like in order to construct this particular filling, you had to make some really careful choices of like how you moved stuff around and like arrange things. I guess I was like curious about if there were other interesting moves that you've looked into that kind of had a similar flavor?
Yeah, so maybe I want to say two things in response. In terms of other moves, I think this has actually shown you most, if not all, the moves that we have actually used. Well, there's another thing which is basically Hurwitz's move. So let me give the first part of the answer, and then I'll give the second part of it. So there's a completely parallel story for studying surfaces in parallel to braided wiring diagrams, which is monodromy factorization. So just like with left twist vibrations, you can encode them as a factorization into Dane twists. Here, you can also kind of encode the surface by factorizing it into factorizing the braid into some product of conjugates of specific braids, which you get as the link of a kind of model for each singularity. So you can, it's maybe some generalization of the Dane twist for left twist vibrations. So there's this kind of monodromy factorization picture, and if you look at that, there's kind of equivalence moves on the monodromy factorization. And kind of the easiest thing you can do is the monodromy factorization is meant to take a bunch of loops that go around the singular points in your plane, or the singular values in your plane. And you look at the monodromy around each loop, and that's each factor, and then the product of all of them is the loop that goes all around the whole thing. So if you sorry, I'm trying to remember. Oh yeah, so the equivalence relation on those, one thing you could do is you can take two loops and kind of switch the order that you do them in. And you have to change the loop so that the product is still kind of the loop that goes all around everything, but that's a Hurwitz move. And so that generates a kind of move that you can do on these diagrams. We kind of did that a little bit by moving some intersection points past each other. But there are generalizations that you can kind of take any two singularities that are next to each other and change their order in some sense at the cost of some braiding. So that's maybe a move that is more general that I didn't specifically show here. I suspect that there should be other things that you can do, and it would be great to eventually have a full calculus for these kinds of braided wiring diagrams. But at this point, it's kind of just like work in progress, I would say. Yeah.
Other questions? I actually have a question. So how do you know that, so you go to, can you go back to the last? Yeah, like the really last one. Why are you done?
Wait, oh, the last of the...
Yeah, so now you see this braided wire diagram, and how do you see that that one is not, is unexpected?
How do we see that? Say again?
That this one is not coming from a Miller.
Oh, yeah, so so what we do here is we do a kind of basic like Euler characteristic calculation. So, you know, if you take this and you turn it into a nearly left-shift vibration, then you can figure out that this is a rational homology ball by just kind of counting like the number of intersection points versus the number of strands and branch points. So that tells us this is a rational homology disk. And then there's a kind of completely independent result about algebraic geometry that says there are no rational homology disk fillings for this class of singularities. And so just kind of the topology is telling you this can't be a Milnor fiber.
Thank you. Any other questions? Oh.
is there any work in partial results, anything in higher dimensions, isolated singularities?
Yeah, I mean, so you could definitely ask the question. There's a contact link, but I think we know so little about symplectic, like constraining symplectic fillings in higher dimensions. That would be challenging, and I actually don't know on the algebraic geometry side. Like this class of sandwich singularities is pretty special that they're able to understand the deformation theory. So even for other kinds of classes of surface singularity, complex surface singularities, it's a hard problem to be able to say anything towards a classification of the smoothings. And I imagine in higher dimensions it just gets worse, but I don't know for sure.
I think I remember that isolated quotient singularities in higher dimensions have no deformation. There's no smoothing at all by deformation. So any Stein filling would be unexpected.
Yeah, that's an interesting question. Yeah, that would be very cool. But yeah, and so I guess you'd only need a construction. And so you could try to work with some sort of Lefschetz vibration picture in higher dimensions, but yeah, it's a good question.
Anyone else? I think no, I don't see anyone, which means that we're going to thank our speaker again. Thank you, Laura. And we're going to have a slightly more than 50-minute break and then resume for our last talk. All right. Then we welcome our last speaker for the morning, Luya Wang, talking about complements of submanifolds in four-dimensional Weinstein domains. Thank you.
Thank you for the opportunity to speak here. So actually, the submanifolds are all surfaces, so I should have just said surfaces. And this talk is joint work with Agniva Roy and Joseph Breen, who is here. So the outline of the talk, I will first give you a motivating problem regarding these objects called regular Lagrangians. I will define them. And then I will, I guess, we have seen these before, but I will actually introduce the notion of nearly Lefschetz perturbations, which came from our existing work with Agniva and also Hyunki. And then I'll give you proof of the main theorem regarding the regular Lagrangians when it comes to that, using the second part, this tool of nearly Lefschetz perturbation. Okay, so let's start with this notion of regular Lagrangians. But before that, we need to have the setting of the ambient manifold, which is a Weinstein domain. I'm only going to work in dimension 4, but this is a general notion. A Weinstein domain consists of the triple, including a Liouville 1 form, an exhausting Morse function, meaning that the regular, the level sets are foliating the Weinstein domain, and a gradient-like vector field associated to the Morse function. We have this slogan by Alan Weinstein, everything's Lagrangian. This is why well, this is not why, but we care a lot about these Lagrangian submanifolds in our symplectic manifolds. And just since this, I guess, is the first time we see Lagrangians today, so a Lagrangian is if a submanifold where the symplectic form restricted to the L is 0. And in the Weinstein setting, since we have this Liouville 1 form, we would like to talk about exact Lagrangians, which is when the Liouville 1 form restricted to L is the D of F is the exact 1 form. Okay, so finally, among the Lagrangians, we want to study, for this talk, the regular Lagrangians. These are Lagrangians that are tangent to the Liouville vector field. And this is in the sense that my Liouville one form vanishes on the Lagrangian. And everything we do here is up to Weinstein 1 homotopy. The 1 here signifies that my Weinstein homotopy, the Morse function associated to the Weinstein homotopy, allows to have birth at singularities. And this is really the notion of homotopy Chilibach Eliashberg already considered, but I just wanted to emphasize there's the allowance for birth at singularities. Okay, let's look at some examples. This is perhaps the most familiar Lagrangian. These are 0 sections of cotangent bundles. Why are these regular? If we look at the Liouville 1 form, P is the cotangent direction, and this is just 0. So 0 sections are regular. And cotangent fibers are also regular, because if we look at the Liouville vector field, these are tangent to the cotangent fibers. More generally, okay, I guess, we have co-course of critical handles. These are also regular because, as you see in the Weinstein handle local model, these Liouville vector fields are tangent to the co-course. And more generally, smooth locus of Lagrangian skeleta. Okay. So these regular Lagrangians are important examples of Lagrangians, and we can visualize them relatively easily. And you may ask, as was asked in the paper by Eliashberg and Lazarev, are all exact Lagrangians with Lagrangian boundary in Weinstein domains regular? So this is asking how common regular Lagrangians are in the space of Lagrangians. Questions? So this is not true in general for general Weinstein cobordisms. In higher dimension, we have Lagrangian caps constructed by Eliashberg-Murphy in R2n minus a ball. They use H principle. And in dimension 4, we have the construction by Francesco Lin. He also constructed Lagrangian caps. And more recently, we have Lagrangian concordance that are not regular. And this is given by Dimitrilo, Rizal, and Golovko. So Lagrangian concordance in Weinstein cobordisms. And I want to emphasize that all these examples are in Weinstein cobordisms with concave ends. So we can still ask a question about whether all exact Lagrangians are regular in Weinstein domains, meaning no concave ends. So this is our theorem, work in progress. We're mostly done, it's just writing. So we prove that all exact Lagrangian disks with Lagrangian boundary in 4-dimensional Weinstein domains are regular. And I will talk about why we need the assumptions on disks and where we will use the assumption of domain. Some history of this talk, of the problem. So this is as in contrast with the previous result, this is a positive result. And similar positive results, I guess, dated back to Eliash-Poterovich. This is really where, I guess, nearby Lagrangian conjecture started. They show that every Lagrangian plane, standard at infinity in R4, is Hamiltonian isotopic to the standard one, the standard 0 section R2. So in particular, this is a regular. They show that every such Lagrangian plane is regular. But I want to mention that there are Lagrangian slice knots that are not the on knot. So our result is non-trivial even in R4. And more generally, we have wherever nearby Lagrangian conjecture is proved or nearby co-core conjecture is proved, these are examples of showing regularity of Lagrangians, although none of the statements are, the settings are different. They cannot care about mostly Hamiltonian isotopies, and also they care about a specific Lagrangian they want to isotope to, meaning either the 0 section or the co-cores. Okay, so I'm going into the second section. Are there questions on the first section regarding regular Lagrangians? Okay. So first, let me review this left shift vibration, which we have seen yesterday and today. But maybe let me just emphasize this bordered adjective, which is different from what Lisa was saying about regarding broken. So this bordered is really just an adjective for the boundary. We require the boundary. So the boundary of this E decomposes into the vertical and horizontal boundaries. And the vertical boundary gives you, in your head, you should be thinking about the mapping torus of the open book. And the horizontal boundary is supposed to give you the binding of your open book. And there's a technical assumption that we require each fiber to be connected and has non-empty boundary in the horizontal boundary, the binding. And this property you have seen. Near each critical value, there are holomorphic coordinates such that the projection map is given by z1, z2 goes to z1 squared plus z2 squared. And pictorially, so the star denotes a nodal fiber or singular fiber, and the regular fibers have essentially the same topology. Nodal fiber has essentially the same topology with a node. And as you go around the green circle around the nodal fiber, you see a right-handed Dane twist along the essential curve in the regular fiber, denoted there in the green circle. Okay, so this is the classical notion of left shift vibrations, or border left shift vibrations. And now we introduce this so-called exotic fiber. So in particular, you see that this exotic fiber changes the topology of the ambient regular fiber. Before it was a cylinder, now it's a disk. But the disk is actually, I drew a doubly covered boundary component, but it's, the whole story actually came from studying pseudo-holomorphic curves in completions of symplectic fillings. So these are the configurations that naturally arise when you consider the SFT limit of the moduli space. So these are just things that come up. But now you can actually study these objects purely in dimension by themselves. So let me define a nearly left shift vibration. A nearly left shift vibration is the usual left shift vibration with a smooth map, finitely many interior critical values and exotic values. And near these exotic values, we require the holomorphic coordinates such that the projection map is z2 squared minus z1. Okay, and then I want to emphasize these singularities at infinity happen near the horizontal boundary. So you see a doubly covered end along the generalization of the binding. So this generalizes rational open book, but it's maybe if you think about it purely as rational open book, you'll get confused. Okay. So here is the summary. We have the usual left shift vibration, which has this local model, holomorphic local model. And the nearly left shift vibration, we add these additional possibilities going from z1, z2 to z2 squared minus z1. Topologically, the singular fibers are just these nodal fibers, and the exotic fibers are these doubly covered disks. And the monodromies, when you go around the singular fiber, these are right-handed Dane twists. And the exotic fibers, these are so-called boundary interchanges. So if you have two, these two are boundary components of your open book, spine open books. And what happens, what's intended to be drawn here is these two boundary components get swapped by pi, and then twisted back by pi to counter the trivialization. So you have a trivialization away from this singularity. Questions? So maybe let me say something more. So these monodromies can be identified with multi-section complements by Baikor and already studied by Baikor and Hayano. And as mentioned, we call these boundary interchanges. And I want to emphasize again, these are monodromies that hadn't been studied before because they move the boundary of your pages. So these are not compactly supported. So let me give you a non-trivial example of nearly left-shift variation. Let's consider B4 minus an annulus multisection with transverse half-length boundary. So this is the annulus in your B4 with the half-length on the boundary. We denote the zero handle. Let's talk about the one handle first, which is the red part, and the zero handle, which is the disk outside of the one handle of the annulus. And by, we learned in Gonfan Stiffshits that you can do a dotted 1-0 handle replacement to look at the complement of this annulus. And this is the diagram. And you do some rearrangement and get this. And you do some further arrangements. And then you Lagrangian realize to get a Weinstein picture. And this is actually a very non-trivial example of Weinstein domain. This is interested by the, mirror symmetry, homological mirror symmetry community. This is a self-mirror object. Okay, and there's a bonus slide. I was hoping the notion of spinal open book will be this. Oh, I guess Gordana mentioned it briefly. So if you want to study the spinal open book on the boundary, on the contact boundary of this Weinstein domain, here, like in the last picture, this has a natural spinal open book, which is given by where the pages are pair pants with two boundary interchanges, denoted by the orange lines, and the vertebra is a union of a disk, which is the usual binding, and an annulus. And I color-coded, so the yellow boundary component, okay, go back. And the yellow component, the yellow boundary component gets glued to the yellow boundary component here, and then, that's okay. And the green one goes to the green one, and the blue one goes to the usual binding. That's just a solid torus. This additional picture is just to tell you that sometimes we are able to find a regular open book for spinal open book, substituting the boundary interchanges. And here it's actually, you can actually see, so this is still not a regular open book, even though you don't see boundary interchanges anymore, where the pages are just represented by this monodromy, because the vertebra is still kind of a non-standard. You have the disc ones, which are the standard regular usual binding, but you still have the annulus binding, which is a phenomena of the spinal open book machinery. Questions here? Okay, this is a bonus slide, so let me just go forward. So recall that, so now I'm going to tell you some extra properties of nearly left-shift variations that we develop. So recall for the usual left-shift variation, so the adjective positive allowable means that you only consider right-handed Dane twist, and allowable means that these Dane twists are on essential curves. These are supported by canonical Stein structures. And there's a long history on people working on this because some people study using Stein structure, some people study using Weinstein structure, and the notion of canonical is canonical with respect to the left-shift variation. So to do that concretely, you also need, there are also some recent development of these. And what we show is that the positive allowable nearly left-shift variations are also supported by canonical Stein structures. So really from the example that I showed you, the B4 minus the annulus multisection, you can arrange the annulus multisection into a complex algebraic curve, and we know that if you take out an algebraic curve out of a Stein domain, the complement is Stein. So this is some general theory. And indeed, so this is the theorem we show, and really to show the canonical part, we needed to build local polar subharmonic charts for the Stein structures, but for this talk, I just want to show you a Weinstein structure on the nearly left-stretch vibration. And this equivalence between Stein and Weinstein structure is given by the deep theorem of Chiliback-Eli-Ashberg. So let's just look at a particular Weinstein structure on the nearly left-stretch vibrations. So by previous works that I mentioned, we already know how to build a Stein or Weinstein structure on a regular left-stretch vibration. You start with a vibration, and then you build. You give a two handle along each singular. Whenever you have a singular fiber. So it suffices for us to consider what happens near an exotic fiber. And this Weinstein structure near the exotic fiber we build by considering the product Weinstein structure given by Weinstein structures associated to these Morse functions, because these Morse functions are going to allow us to glue the Weinstein structure in this model to the ambient Weinstein structure. Okay, and here you see a index 1 critical point and an index 1 critical point on each component, on each factor. And to tell you what's the Weinstein structure, I need to tell you how I attach the Weinstein handle to handle. And this is by considering the boundary of the stable manifold, which I drew here in the yellow line, as a product of the yellow curves. And you can see these are the stable manifolds. And if you plot the boundary of the stable manifold, it's actually, you will see this figure 8 curves near the boundary. These are two boundary components of a regular fiber nearby. Okay, so these two boundary components, as you go close to the exotic fiber, they collapse to 1. And the attaching sphere is going around two of these boundary components. And it's not supported in a single page, but it's supported in an arbitrary small neighborhood of the page. Okay, so this is supposed to tell you what a Weinstein structure looks like on a nearly left-stretch vibration. Questions? Okay, yes?
I wanted to ask this earlier, but I just thought I'd double check. So these exotic fibers, they're always doubly covered? Okay.
Topologically, you're just supposed to think of them as a disk. And the double cover comes from when you glue the mapping torus to the spine area, then two boundary components are glued to one.
Okay. Okay.
Yeah.
So it'll wrap around. When you do the gluing, it wraps?
It's not really wrapping around, it's 2 to 1. The two boundary components goes to 1. Yeah.
Okay, okay. Great, thank you.
Yeah, that's why I kind of said the rational open book kind of it's a confusing analogy, I guess. Yeah. Okay. Further questions? Okay, if not, then you can still interrupt me regarding the previous sections. But now let me try to show you a proof of the main theorem showing all exact Lagrangian disks in Weinstein domains are regular. So let's start with an exact Lagrangian disk in a Weinstein left-stretch vibration. We started with a Weinstein domain, and we get the left-stretch vibration by Giroupardin, or in dimension 4, done by Loïc Pigarlini, Akulu Osvaji, and Plemenevskaya. So this is the picture. We start with this left-stretch vibration, and we have a Lagrangian. I drew it as a multi-section, but this is what we want to prove. So there's some Lagrangian sitting inside of it with the Lagrangian boundary. And now we push off the Lagrangian disk to be a symplectic disk with transverse boundary called S. So this is some algorithm that you can, that's a combination of Eli-Ashberg and Tal, Galeb, Hayden, and Sabloff. You basically just do a cutoff function near the boundary to make the boundary symplectic, and then Alioshberg tells you that you can do it across the whole disk. So now you have the symplectic disk, which is called S, with transverse boundary, denoted by this partial S. We can do Weinstein stabilizations to arrange this partial S to be a Rabe orbit of arbitrarily small action. So what we actually do here is we arrange this transverse knot partial S to be a binding component. So and this is, we're using an algorithm by Baker, Ettenmeyer, and Benholm-Morris here. And the arbitrarily small action part is going to be needed because later we're using an argument of Symplectic curves, and having smallest action is very nice. It tells you that, it gives you a lot of control on the compactness of the moduli space. Okay, so this S now is a symplectic disk with Rabe orbit on the boundary of the smallest action. We want to make this a symplectic multisection, again via Weinstein deformation, but Weinstein homotopy. And in B4, this is the classical work of Boiler-Arevkov, although I want to emphasize that we don't actually know how to show this, making a symplectic surface in Weinstein domain a multisection in general. There's some index computation here of S that requires the knowledge that S came from a Lagrangian disk. So the proof idea of such a statement is to find an almost complex structure, J, that makes both S, which is your symplectic surface, and the fibers of the left vibration, J holomorphic. So it's this picture. Really what you do is you first find a JS that makes the red surface JS holomorphic, and then you find a JF that makes the fibers holomorphic, and then you go from JS to JF. And since the partial S is of smallest action, and we're in a Weinstein domain, there's no bubbling and possibilities of breakings, so this red disk persists. So then JF would be the almost complex structure that makes both S and the fibers J holomorphic, and then you can see that L is actually a multisection. So some remarks here that we actually used the fact that the red surface is a disk because of some, there are two parts because automatic transversality when you consider this family of J. And then we also need it because it makes analyzing the possible breakings easier. And then we also use the fact that this is a Weinstein domain because otherwise there are also more possibilities of negative breakings, breaking into negative levels. Questions here? So yeah, this is a pseudo-holomorphic holomorphic curve step that we leverage. Okay, I'm going to end very early. Then in the end, we already, what did the previous step tell us? So S is a symplectic multisection in the Weinstein domain. So the complement of it is what we call the nearly left perturbation. And by our theorem before, stating that these objects are supported by canonical Stein structure, but we just needed one for this proof, that we know these complements are supported by Stein structures. And finally, since the complement of the symplectic surface is Stein, this tells us that the complement of the Lagrangian disk is also Stein. And this is using, sorry, the yellow part is a bit opaque, but this is using our understanding of what the construction of the Weinstein handle near the exotic fibers, because the Weinstein 2 handle, the attaching sphere for the Weinstein 2 handle around the exotic fibers, these are compact things, so you can actually make all the critical points of the associated Morse function on your Stein domain away from this symplectic surface that's cut out. Okay, so then there exists a Lagrangian neighborhood that encompasses the symplectic neighborhood, so you can use this complement of the Weinstein structure on the symplectic neighborhood to get the Weinstein structure on the Lagrangian neighborhood, complement of the Lagrangian neighborhood. Okay, so now we have the fact that the Lagrangian complement is supported by a Stein structure in the left perturbation, in the original Weinstein domain. And this tells us that L actually sits as a co-core. So you take out this L, you still get something Stein. Using that L is also a disk. This tells you that L is a co-core in the original Weinstein domain. And by our definition of regularity, this shows that it's regular. Okay. And yeah, actually, this is the end of my talk, so we can wrap up and then.
We are a bit early. Thank you for your talk. Any questions? We have a lot of time for those.
So you mentioned multi-sections. Is it this multi is 2 or could
It's a what?
These multi-sections intersect the fiber twice or more than twice?
Sorry, so intersect what? Sorry, what? Twice? Oh, yeah. So these are generic multi-sections, meaning that it's 2 sheets coming. I only consider generic branch points, simple generic branch points, 2 to 1.
You don't have to consider like D to 1 or?
You can always do a local perturbation to make sure that you're not in that setting. Yeah, Weinstein homotopy is a very flexible notion, so you can do a lot of things locally. Yeah.
So you can make all the branching points simple, but is it globally a two-fold branch cover, or I mean, is it globally a two-fold cover, or just locally?
Oh, just locally, yeah.
Any other questions? Well, then thank you very much. Then we can all go for lunch, and we resume at 3 o'clock. Don't forget that today is picture, so come back for the afternoon. And, yeah, of course, as always, please sign the registration form. We need the signatures for reimbursement, okay? Anyone who hasn't, please. See you at 3.